Today we're going to talk about the binding ratio, which is also known as the 2-to-1 rule. First, we're going to demonstrate what exactly the binding ratio is. Then we're going to talk about the math and engineering principles behind the binding ratio. And finally, we're going to show a whole bunch of examples which should further demonstrate and explain the binding ratio. So let's jump right into it. In front of me is one of our classroom demonstration units, featuring our Uniguide sliding table. The binding ratio is a mechanical principle which relates the bearing length, or in this case, the length of the carriage, to the maximum moment arm distance where a force can be applied, which will still result in motion. Now I'll demonstrate this principle using the unit in front of me. I'll go ahead and use this carriage here. I'll apply a single force at the carriage. As you can see, the motion is smooth. If I apply a force with a small moment arm distance, the motion is still smooth. It doesn't matter if the force is small or if the force is large. Now I'll apply the force with a larger moment arm distance. As I do that, the motion begins to go from smooth to jerky to no motion at all. This is the basic principle behind the binding ratio, or the 2-to-1 rule. And it doesn't matter if the force I apply up here is small or if it's really large, the result is still the same, binding. It's not going to move. We'll apply a force at any distance d1. Newton's third law of motion tells us that there will be equal and opposite reaction forces which keep the carriage from spinning. These forces appear as forces F2 and F3. Since the carriage does not spin out of control, we know the sum of all forces about the center of the carriage at point C is equal to 0. The whole purpose of a linear guide is for motion. And basic engineering principles also tell us that wherever there's motion, there's also friction to resist the motion, which appears now as forces F4 and F5. To calculate the actual values of the applied frictional forces, we can assume that we either know or have design control over the bearing length, the moment arm distance, and the type of bearing, and therefore the coefficient of friction. We can then create a free body diagram and use basic statics equations to calculate the actual values. At a transition point, the frictional forces will exceed the applied force and movement will cease. This is a basic theory behind the binding ratio. In reality, as engineers, we don't really have any control over the applied force, as the application dictates this value. We do have control over the size and shape of the bearing system which we choose. If we go back and look at the example again and leave everything as a variable, we can simplify the equations down to a set of conditions which have to be satisfied in order for motion to exist. Interestingly enough, notice how the applied force does not show up in any of these equations. This validates our earlier experience where it didn't matter if I pushed with a small or a large force. The only variable which appeared to matter was the binding ratio. One variable that we did not discuss earlier, but now appears, is the coefficient of friction. So let's look at that in more detail. If we only focus on the equation at the bottom of the screen, we can look to see how the change in coefficient of friction affects the binding ratio. The graph on your screen shows the binding ratio as a function of the coefficient of friction. The graph shows that the larger the coefficient of friction, the larger the binding ratio can be. In practical terms, this means that for applications which have a large moment arm distance, we need to either choose a bearing system with a low coefficient of friction or have a counterbalance to help reduce or remove the moment load. I know we skipped through all the equations which provide the empirical proof for the binding ratio. If you're interested in seeing the math and learning more, you can download a free white paper from PBC Linear's website at www.pbclinear.com. Now that we've discussed the engineering principles behind the binding ratio, let's explore some real-world examples. In front of me is the same demonstration unit that we used earlier. The front two rails have the same product, the only difference is the carriage length. Using what we had just learned, we would expect a longer carriage to have a longer allowable moment arm. Let's see if this holds true. I'll start with the shortest carriage. I'll apply force at different lengths until I reach the point at which the system binds. I'll start by applying force at the carriage, and then work my way up the shaft until I get to a point where motion stops. As you notice, as I move up the shaft, the motion begins to stutter, or we see some stick slip. Finally reach a point at which motion stops. And it doesn't matter if I push with a small or a large force, this is the binding point or transition point. I went ahead and marked this with an O-ring so the camera can see it easier. I'll move on to the next carriage. This carriage is a little bit longer than the first one, and we would expect that the binding ratio would be a little bit longer on this one as well. I'll apply a force at the carriage, and then I'll apply a force moving up the shaft. Eventually I reach a point where motion begins to bind and stop. And again, it doesn't matter if I push with the hard force or light force, motion doesn't exist. I went ahead and marked this spot with an O-ring as well. Moving on to a third carriage, which is a little bit longer. Again, we would expect that the binding ratio, the allowable moment arm length, to be longer still. I'll apply force to the carriage, and it's nice and smooth. I'll work my way up the shaft, and again, it's still smooth. So not until I get to the very top of the shaft, I begin to see some resistance, and the binding ratio, or the transition point, is actually probably right up about here, a few inches above the top of the shaft. So I went ahead and marked it at the top of the shaft. I'll move on to the fourth carriage, which is even longer still. This carriage I'd expect not to be able to get the system to bind. I'll apply a force at the carriage and then up the shaft to the very top, and at the top of the shaft, motion is still smooth. The binding ratio, or the transition point, is well above the limits of the shaft. I'll go ahead and position them all so the camera can see them. And what we notice is that the shortest carriage has a binding ratio, or an allowable moment arm, which is about a third of the way up the shaft. The second carriage has a allowable moment arm, which is probably about 2/3 of the way up the shaft. The third carriage has a binding ratio, or transition point, which is somewhere near the top of the shaft, probably a little bit beyond the top of the shaft. The fourth carriage, which is the longest, I can't even begin to find the binding ratio, or the transition point, as the transition point is probably a few inches or maybe a foot above the top of the shaft. Not yet explored is how the coefficient of friction affects the binding ratio. Let's look at a different classroom demonstration unit. The unit in front of me has many different products on it from PVC, as well as some from other manufacturers. Some of the products are plain bearings, some are recirculating ball-based linear systems, and some are cam roller-based systems. Let's take a look at the different coefficient of friction and bearing length and see how each of those affects the binding ratio. The first one I'll start with is a 2 parallel shaft pillow block based system. This system in front of me, the first carriage has linear ball bearings in it. The second has a plain bearing system from a different manufacturer. And the third has PVC linear simplicity bearings inside of it. The first one is a linear ball bearings. This is a very low coefficient of friction, and it slides easily, even when I apply a force all the way to the top of the shaft. The second system is a plain bearing system made from another manufacturer. This system has a much higher coefficient of friction than the linear ball-based systems, and it has a higher coefficient of friction than the simplicity bearing. So let's go ahead and see what happens when I apply a force at different lengths. First, I'll start off at the carriage, and then I'll work my way up the shaft until I get to a point at which the system binds. And I've gone ahead and I marked this with an O-ring so that the camera can see it. Secondly, I'll move on to the simplicity-based system. I'll repeat the same experiment, applying a different force until I find a point at which the system begins to bind. I marked it also with an O-ring. As you can see, that the lower coefficient of friction leads to a higher binding ratio. So we have three systems in front of us. The linear ball-based system has the lowest coefficient of friction. It also has the largest allowable moment arm. The next system is the simplicity-based system. Its coefficient of friction is higher than the ball-based system, but lower than the competitor. Its allowable moment arm is higher than the competitor's bearing. Let's move on and talk about a few different types of bearings. Let's look at probably one of the most common types of bearings found out in application. That's a profile rail, or linear recirculating ball-based system. This system right here is very stiff and has a very low coefficient of friction. I can apply a force at the top of the shaft, and I experience no stick slip and no binding. Next, we'll move on to our ReadyRail product. The ReadyRail product is a cam roller-based system, and it also has a very low coefficient of friction. I can apply a force at the top of the shaft very easily, and it'll move without binding or without stick slip. The third product is PVC Linear's commercial rail product. I can apply a force on this one as well at the top of the shaft without any problem. This product also has a very low coefficient of friction. Next, I'll move on to PVC Linear's low profile slider LPM series of product. This product is a plain bearing system It has a higher coefficient of friction, but it's also sloppier in the rail. The precision is less than the products we were talking about earlier. I can apply a force on this one higher up on the shaft and still get it to bind. However, if I apply a higher force, it binds more quickly. The reason for this is the slop, or the play, between the carriage and the rail. Next, I'll move on to PBC Linear's Uniguide. We've already talked about this one earlier in the last demonstration unit, and the same principles hold true. I can get up to probably about 2-to-1 with very easily movement. When I get up to 3-to-1, I still have a little bit of movement, but the force is a little bit higher. When I get up to 4-to-1 or 5-to-1, it begins to bind and not move. Next, I'll move on to some more plain bearing systems. The first is a competitor's product made up of several different types of components that are all screwed together. If I apply force at the bottom of the carriage, it moves, but I can feel that there's quite a bit of resistance, so I know the coefficient of friction is a little bit higher. I apply force up the shaft until I get to a point where it doesn't want to move, and that's the binding ratio. Next, I'll move on to a new product from PBC Linear. It's a low-profile Uniguide, very similar to the normal Uniguide, just smaller and happens to be size interchangeable with the competitor's product that we just showed. If I apply force near the carriage, it moves very smoothly. As I move up the carriage, because the coefficient of friction is lower and the precision is greater, I'm able to get higher up, and I can still move it. It just begins to stick slip a little. You compare the two and see that the lower coefficient of friction yields a higher binding ratio. Next, we'll move on to some more products from PBC Linear. I'll move on to the end. In the end, we have a rail that has two carriages on it. The first one, and the one in the back, is a plain bearing system for mini rail. The second is a cam roller based system. The carriages are the same length, so when I apply force near the carriage, the motion is smooth. As I move up the shaft, I begin to get some stick slip. As I move farther up the shaft, eventually I get to a point where the system binds and no movement's allowed. One nice comparison is that because these systems are riding on the exact same rail, the carriage length is exactly the same, and this one I can apply force all the way to the top and it still moves. This helps further demonstrate the differences between the mini rail product, a plain bearing system with a high coefficient of friction, versus a cam roller based system with a much lower coefficient of friction. Thanks for taking part in today's online class.
Learn more at pbclinear.com.